of indefinitely divisible law. The probability mu on R is a law, I mean, if you are probabilist, you call that a law. And it's called indefinitely divisible if for all n you can solve mu, the equation where the power is the convolution power. So if you can write mu as a convolution of n identical, of n times the same other probability on R, you say that it's divisible by n and indefinitely divisible if you can solve it for all n. And what does that mean in probability? It's very natural, because it means that mu can be written as a sum of n independent random variables in the distribution mu. That's something which you can encounter often in probability. So what's happened on R? So indefinitely divisible probability has been classified completely on R by Levy and Tucci in the almost 90 years ago. And they describe the Fourier transform of a law which has a problem. And it turns out that we can also describe the Fourier transform of the probability which can be embedded in the semigroup. And they are the same. So it's not the same a priori. Yeah? You can solve individually for each n the equation mu n equal mu, and to be embedded is saying that you can solve simultaneously with the same family and with the same family which are arranged in a semigroup. So that's the question of. So it turns out that for R, they are the same. As soon as you can solve the finite equation, I mean it's like in number 12, as soon as you can solve the finite equation at each stage, you can solve the equation on the real life. And it was shown for locally compact Laplace-connected abelian groups that the same is true. The same is true, but it was shown independently. Hunt described the semigroups, and Sayajirao and Baroda described the infinitely divisible law. And it turned out that they were the same. So the conclusion of that is that any indivisible law on a locally compact Laplace-connected abelian group is embeddable. You can extend, you can find a semigroup of probabilities, a convolution semigroup which gives you the same group. And after that, you ask the question, in fact, Sayajirao has the question, that is it true that on any locally compact group, or you can find an indefinitely divisible probability will be embeddable into a semigroup. So it's a question, and it will be the thread of the talk, because there are several results, and many results which are known about this question, and most of the results, Krishna and Dani, have something to do with everything which is known about it. And in fact, 5 years ago, for his 60th birthday, there was already a talk on the same topic, and for more technical presentation, I will refer you to that talk, which, I mean, you have to ask Klaus, because I don't think it's available on the web anywhere, but that's a good reference for the state of the art up to December 2007. So the question is simple. You have a probability on a group. So it's very natural. I mean, you can make convolution. You can solve the equation for each integer. And the question is whether you can find a continuous family which will be a semigroup of convolution, and which at time 1 will give you your name. So what are the obstacles? So one obstacle is connectedness, or I mean one counter example, the thing which is not true, which I understand, is you take the Dirac measure on 1 on Q, then it is infinitely divisible. I can put the Dirac measure on 1 over n, and if I convolute n times it gives me the Dirac measure at 1. But of course, there is no way I can put a semigroup on Q such that the time 1 is a Dirac measure at 1. So that's a problem. It tells you that there is a problem with connectors. As soon as it. And it's very vague what I say. What I say here is vague, but it's essentially correct. That in some sense, it's the main obstacle that connectedness presents. A more precise statement would be that each time you have some reasoning which gives you some result for connected group, then you can extend it for locally compact connected group, and then you cannot extend, but the same reasoning would give you something for non-connected group, and there are many results which are valid also for group of group. It's not that it extends, it's that the same reasoning still works, typically. Modulo taking care of some counterexample which can arise if the group is not connected. So, I will talk only about connected groups. I don't give precise statements. It would not be meaningful to give them more general setting. So what you want to do? I mean, I have, for each n I can find mu n, such that mu n convoluted n times is mu. So if I can try to take all this mu n in a coherent way. I mean, if I take a multiple of n, and then I will try to take the one with mu n, which is the one with the power n of mu n n, something like that, and at least to construct an embedding of Q, a semigroup indexed by Q, such that the time 1 is vector 1, and hope for some continuity or some compactness to go to the code. I mean, that's what one wants to try, but there's something which can go wrong in that scheme, is that you have no compactness a priori on the set of solutions. So you have solutions, but they can go to infinity. They can go away because assume that you have an automorphism which preserves mu. Then clearly, if you have a solution, the same automorphism would send the solution to another solution. It's an automorphism of the group. It commutes with convolution. If you have a solution of the convolution equation, I apply the automorphism to both sides. Mu is invariant, and here I get another one. And I reapply the automorphism, I get a whole family of measures which can go to infinity, and just for that reason, already for that reason, there is no reason that the set of solutions is compact. So if it's not compact, I don't know exactly how to go to the limit when I start building my approximate solution for finer and finer sets. And okay, the main answer to that question is in two papers. In fact, one on 92 and one much recent in 2007 of Dani and Maharaja, which say that in fact this non-compactness exists. It's really an obstacle, but it can be controlled. It can be controlled in the sense that you see where it comes from. It doesn't come from any kind of automorphism that you can think of. It comes really from very particular automorphism, the one which are given by inner automorphism for which are the connected components of the centralizer of the problem Q, and not only in G, but in the commutator of the code. So all the other automorphism, in some sense, can be reduced to this one. And we'll see vaguely why. So, but that's not for all groups. As you might imagine, if I get such a result, it means that I lose some result of group structure. And in fact, you can do all this reduction only for some class that they introduced for the result, and it's the famous class C. And for class C, in fact, you understand what happens. You understand what happens, the way of going to infinity, the way of losing control. In fact, it's very nice because it's elements of interior automorphism in that centralizer, and you can work with it. You can work with them, and the result is there, but maybe I should say before, what is the connected group of class C? So connected group of class C, if it admits a finite dimensional real representation with discrete term. This is quite general. And from the result, from the two papers in 92 and the recent paper in 2007, in fact, from class C groups, the embedding problem is solved. And in fact, it's almost solved in general. What terms, when they can reduce to some compact part which you cannot control. And one consequence of the result is the following theorem, is that if you have a connected group, and if you have an indefinitely divisible probability on G, then you can find the compact abelian group such that if you saturate your measure by the compact abelian group, and it will be the same to the left and to the right, and that new measure is embedded. So in some sense, all your problem comes from things which are compact, and of course, in compact, it's not you have the hard measure of a compact group. It is indefinitely divisible because it's always divisible by itself. It is embeddable in a semigroup. The semigroup is always itself, but it's a semigroup which at time 0 is not trivial. So you have to decide exactly what you want to do. Okay, so what do you want to say? So what did I say? I said that in fact the problem, one of the problems, and it turns out that the main problem, and that's the thing that you can, it is the main problem, two aspects in the theorem of Dani and Maharaja. It is the main problem, and in fact that problem can be controlled. And the problem is to understand how automorphism of groups can go to infinity. And we are talking about B group and by some structure theorem. First, try to understand what happens on linear groups. And okay, we have automorphism, and so we can first try to understand what happens on matrices. Already, what does that mean that a set of matrices go to infinity? How does it translate on the behavior of the matrix? That's something which is very basic, and we had earlier. I mean, we want to understand linear mapping of the finite dimension. And there is a very nice paper by Dani on from a conference with one data years ago, and he discussed this point and it connects with the different other probability of groups. And in some sense, there are many questions on probability of groups which were suggested by this embedding problem, but which are interested by themselves. So what is the setting? Look at two real finite dimensional spaces, and you have a sequence of linear maps from E1 to E2. Really very simple setting. What does that mean? That a sequence goes to infinity. And that's something which is very familiar for people who do quantum walk on groups. I mean, it's really something which has been used also a lot by understand that in fact you understand what it means to go to infinity. There are the vector for which you converge, and the vector which are I can go quicker, and the vector which and the vector such that if it does not it goes to infinity. I mean, converge it might go to 0. Right? But there are the vector for which the image converge, and the vector for which the image goes to infinity. I have taken a subsequence where a priori it's only a subsequence, but I already looked at the relevance. And then a slightly more subtle property, we have the vectors such that maybe they go to infinity, but you have a sequence of vectors which approaches them, and the image of those vectors converge. So in that case, you still can say that they go to infinity, but they don't go to infinity. Alpha k w doesn't go to infinity uniformly around W. Because I mean, there is a way of approaching W and cancelling, if you want, the direction you go to infinity. And that's what happened, and that's it. I mean, that's there are good vectors for which it converges, the one for which it goes to infinity, but nevertheless it converges, and that's the thing you have to understand. So you have a sequence of linear maps from U1 to U2 for good subsequences, and you take subsequences, and you have subspaces, pair of subspaces. So what does that mean for probabilities? If you have probabilities now on the first space, and you suppose that the probabilities converge, and the image by the automorphism converges. Converge to a probability. But to say converge to a probability. Of course, if it goes to infinity, it converges to 0, but that's not what. And the image of the probability converges to a probability. So necessarily, the support is contained in W. And the W was the space of vectors that do not go to infinity uniform. They go to infinity, but not uniform. And now, if you can say for another reason that the support of lambda spans the whole space, then conversely, you can deduce that the automorphisms are bounded. So it gives you a criterion, qualitative criterion, if you want, to see that the alpha k are bounded. And for our problem, you remember that was the question we wanted to control. But I mean, it's interesting by itself, and modulo other steps, of course. There are consequences of the results. One consequence is that it's called the convergence of types. So you apply the preceding proposition to the sequence of automorphism and to the sequence of inverse. What does that tell you? Suppose you have a sequence of probability. You have a sequence of automorphism, and you have a sequence of probabilities such that, on one hand, lambda converge on the same space, and on the other hand, the image converge. So then, by applying the proposition to both alpha and its inverse, if the support of both measures spans V, then alpha is bounded, and alpha is bounded as automorphism, and alpha inverse is bounded. So alpha is bounded in the linear way. So it's a nice term which tells you that you have an equivalence relation on probability. That they are image one of another by automorphism, and in some sense, it's a asymptotic result on that equivalence of type. And using a lot of structure theory, there is this following consequence. I mean, I state a theorem, I don't explain why it follows from the previous, but I hope you feel that it is in the same spirit. And it turns out that there is a technical condition which will come back often. So if you start with a connected Lie group, and you assume that the center has no torus, no torus of co-positive dimensions, so no compact subgroup. Now, for a probability on G, I can consider two sets. The set of automorphism which preserve lambda, that's the bad guy that we had at the beginning, and the guy which is more, which is still bad, but we understand, I mean, we have a lot of structure on it. The set of automorphism which respect the support of lambda pointwise. Of course, G of lambda is a normal subgroup of I lambda. And the proposition is that the quotient I of lambda divided by G of lambda is compact. Will this explain why I mean, the enemy at the beginning was I of lambda, but in fact, in the theorem of Dani and Macmillan, we can reduce to automorphism by elements which, in fact, commuted with the supporter. Why? Because the quotient is compact. How you get the quotient is compact? Modulo understanding the structure is by this boundedness. Using among other tools, this boundedness. Okay, that's one thing, and clearly it enters the embedding theorem, but it's interesting by itself. So another statement is something which is also well known in probability for low probabilities, also for measure on R, is to talk about the concentration function. So you take a probability on group, the compact group, better. And you take a compact subset of it. And now you look, the concentration function is how the measure is concentrated on the image of the group. So it's not so you want to it measure, you don't know exactly where, but you say that I fix a compact, I fix some size, and I want to see whether somewhere in the group there is a neighborhood of that size which carries some of them. That's why we call it concentration. And you say that the measure is scattering if, in fact, when you take the powers of convolution, it's less and less concentrated. Again, if you take the R measure of the compact group, it will keep being the R measure and it will not be scattering. But if you take a nice measure on R, it will be square, and the density will go to 0, and it will be scattered. So it was the example I think, maybe a little more elaborated. If you look at the support of group. If you have a compact normal subgroup and mu is supported by a coset of that subgroup, then it cannot be scattering, because I mean, if I take the convolution, it will be supported by another coset. So that's exactly what I'm asking for. I'm asking the sup of the measure of the image of my compact. So all the images will be supported by coset, so it will not be And again, following from the characterization of bounded subset, there is a kind of converse. That if you have a probability which is not scattering, then you have it is concentrated in some sense in a coset of not a compact group, it would be too nice, but an open set. So again, it's kind of a converse of the natural question, and it enters also in the discussion about the embedding. Another classical probability notion is the notion of lazy mode. So a probability measure on a group is called a lazy measure. If it is a weak limit of images of J convolution, so you can take a translate, you can take the image by anthropomorphism, and here I take the convolution of some probability, but probability which are individually, they are carried by alpha to something which is very close to the identity. So the lazy measure, the property of the lazy measure comes uniquely sometimes from the convolution. Individually, the alpha gi, alpha I lambda, alpha I lambda 1 converges to Dirac. So gi, alpha I lambda 1 converges to gi. The lambda 1, lambda 2 also converge to Dirac. So gi, individually, if I look only a finite number of lambdas, it converges, it's concentrated to a point. It's not like move, which I can move, but it's concentrated to a point. So if you have a limit of that which is not concentrated at a point, it means that it carries itself the fine structure, the infinitesimal structure of convolution. And of course, it's a kind of probability measure which occurs as limit low in probability if you are on R, but it makes sense on limit. And it's a result of Dani and Schmidt that, in fact, on a Bayesian group, the limit measures are infinity. So what I was vaguely saying, that those measures carry into themselves the structure, the infinitesimal structure of the convolution, in fact, has a really complete sense, at least on Abelian. And so it's almost so if you have infinitely divisible measure, it's almost like that with alpha gi E and alpha I identity, except that you don't assume that the lambda G converges uniformly to the identity, to Dirac at the end. So, what do they do? I mean, if they don't confirm, it means that if you have infinitely divisible measure, in some sense, you have a liquid measure, but you also have a part which doesn't come from identity and which comes from some compact action that you have to explain in some way. But still for a lazy, still for a lazy measure, everything happened, in fact, I'm going to close this potential. It's the result of Dani and Richard. Are we talking about that tomorrow? No. You will not know why. If you have a Levy measure, then there exists a closed nilpotent subgroup. In fact, the Levy measure, I recall a Levy measure is a measure which is obtained by convolution of things which are closer and closer to the neutral element, not to the transmission of the quantity, but things which are purely convolution in some sense. So a lazy measure is supported by a coset of a closed potential. So indefinitely divisible measure, okay, they are lazy measure plus some compact foam around it. So already, I mean, what we understand from this is that good part of the action, the action which is the most interesting, the one which comes from the convolution, will be restricted to a closed interval. And okay, so what does that tell? It tells that to solve the embedding problem, you have two good news. You have good news and bad news. The good news is that in fact you should concentrate on the nilpotent part. That's what's come from the linear chart. It's great. And the bad news is that you are not exactly knowing what happens with the compact. And after all the work, what they realize is that, I mean, the enemy, I mean, the simplest enemy that they still had, I mean, the simplest guy for which you didn't know in 2007 what can be said, is what they call the walnut group. And walnut, it's because it's hard to break. I wonder sometimes why it's walnut, but in fact the reason is it's hard to break. And the simplest walnut group is this one, and the simplest group such as the center of the radical contains the growth of the dimension. It's just a skew product of n, which is the quotient of the Heisenberg group by the integer on the center, and the circle just act by rotation on the xy plane. So that's a four-dimensional group, and it's apparently it doesn't enter in all the techniques that I've explained so far, but there is a nice theorem which just appeared by Dani, and Schacht, which answers, opens, closed many more cases, and in particular the one group. And the theorem is that if you have a connected group, and if you look at the radical, if a measure is infinitely divisible and supported by the radical, then it is embedded. And I mean, you have, if you want details, you go to the ladies' talk. And happy birthday. It was a pleasure to